So the rest of the lecturing today about differential privacy will be maybe a little bit boring to some extent, but I'm trying to incorporate working examples along the way. And hopefully you got the chance to read about the handout that I shared. And then in class we are elaborating those ideas a little bit more. And then of course, any kind of questions you have, welcome to speak up, and we will have some discussion question break points. Okay, so the conventional traditional differential privacy is focused on adding noise to summary statistics. Okay, and I'm highlighting a few terms that we're trying to define it one by one throughout the lecture today. The key idea is to add noise to the output of queries made to databases. Okay, so those highlighted words in red, we're gonna define it one by one. But the key here is at the end of the day, you're trying to add noise. Okay, you're adding noise to the output, and the output you can think of them as summary statistics. Okay, and the output of queries, so there will be certain queries made to databases. So output are from the queries, and then instead of giving the output directly, because the direct output, I should say, of queries made to databases will compromise privacy. And instead of giving the original output, we are adding noise to the output before release. And then in the end, we release the noisy output, okay? The noise itself is random, okay? And it will depend on predetermined privacy budget and the type of queries. So privacy budget is another key term in this field. And we will talk about it as well as we get to that point. So at the end of the day, keep in mind that we're adding noise. Okay, we're adding noise not to data itself. We're adding noise to summary statistic output, and it really depends on what kind of databases you're working with, and then what kind of queries that you want to know about. Okay, so keep those in mind. And I'm gonna try to define it one by one based on the logic that I think is hopefully intuitive enough. So first of all, let's define database. Okay, so databases are data sets that analysts use for analysis. Okay, so think about databases as confidential. They are the ones that we don't release. Okay, and so in that case, the question becomes whether and how the data analyst can get information of quantities of interest. Okay, since the databases are confidential, they don't have access to it. So instead of, I guess, working with the original confidential data set, what they do is they will send queries. Okay, send questions. You can think about send questions, quantity of interest to the databases. So we're gonna define queries in a second. And so stay on database for one more minute is, well, once the databases are confidential, think about, so from the data analyst point, they definitely still want to get to know certain things that they want to know, right? But then from the data set or database holders point of view, like people like us, for example, if we have the confidential data, then whatever queries or questions data analyst made to the database, well, we will have to provide information based on the questions that they ask, right? And we want to make sure that the output, okay, the answers that we provide, they're useful and privacy protected. Okay, so this is, I mean, if you think about the two angles, right? In the synthetic data field, when we're talking about it in the past, we're thinking about from the intruder point of view, right? And also the data set holder point of view. Okay, so what is special here, as you can see, is that in synthetic data, what we're trying to do is we are generating synthetic data from a model, and we release the data, and we let whatever the user want to do with the data, right? Like we release the data and the synthetic data, and as we have been doing it so far, we release the data that will have the same dimension, right? Like if you have 10 variables you start with, if you have 1,000 observations that you have in your original data, then the synthetic copy of it we produce based on models will have the same dimension, right? And it's actually a good feature because we sort of allow the users to make infinite number of questions. They can do whatever they want to do about the data sets themselves, as long as we release the synthetic data that it satisfies privacy guarantee, right? But here in differential privacy, especially thinking about database, and then soon we're going to talk about queries, it's in the way that, well, we're never going to release the data in this way, right? We are really just doing a case by case that now as the data holder, maybe the data analyst comes along and asks questions about it, about the data set, for example, and then we will have to produce an answer for them and in a useful and privacy protected way. Right? So this is the biggest difference as you move forward. And you will see that, well, if you are able to release synthetic data, satisfying certain privacy guarantee, then you don't even need to worry about what the user want to do, right? The data analyst, you can let them do whatever they want to do. But of course, doing that as we have done so far, we have to evaluate risk in the way that is highly depending on our assumptions. Okay, so here, the differential privacy approach is that, well, we're going to start with a fixed privacy budget that you should not go beyond it, in a sense that, well, I know a predetermined privacy budget, and then for the database holder's point of view, then I will be more restricted, of course, because we're never going to release the data itself, but we are able to satisfy the privacy guarantee more formally. Okay. So we're just going to come back to the CE sample, our old friend here. Suppose here, this is the confidential database. Okay, so this is slightly different from before. We are assuming that the intruder, or not the intruder, sorry, the data analyst will never have access to this. Okay, so we are the only people having access to it. We're not thinking about generating synthetic data. We're just thinking about now we are the holder of the data, and then the data user are going to make certain questions. They send questions to us, and then we have to think about how can we provide answer in a useful and privacy protected way. Okay? Just to get us started, let's just say in this sample, let's just say the analyst is interested in the number of rural CUs in this sample. So I think this sample has close to 1,000 observations, I think. And the urban-rural, if you remember, the first variable, the binary variable here is binary. So it's urban if it's 1, and then it's rural if it's 2. And so basically, let's just suppose the intruder wants to, not the intruder, I have to be a little bit careful. Let's just say the data analyst wants to know about how many, in this case, I guess, how many observations have urban-rural variable outcome as 1, right? Because they want to know the number of rural CUs in the sample. So this is a possible quantity of interest that the data analyst wants to know. And as the database holder, privacy database holder like us, we have to think about way of giving out that information. All right, so the next part, next definition. So now we know database. Okay, the definition here is the query. Okay, so mathematically we denote numeric queries as functions f. Okay, so you can see that we are mapping databases to k real numbers. Okay, so from left to right, the arrow. Okay, so the outcome, the output is r of k dimension. So k. In our case, if we're thinking about the number, if you remember the number, what was it? The number of rural CUs, right? So in that case, it's actually a scalar that the query is asking for. So k is 1. Okay, in our example. Okay, so send the following query to the CE database. How many rural CUs are there in the sample? So k is 1. But sometimes the query might have multi-dimensions, so the output might be k real numbers. Okay, so more generically, it's r of k dimension. All right, so here will be a good time to break for discussion. As the database holder like us, can we give out the actual values? Why or why not? Okay. So yeah, this is just brainstorming. In what way you think giving out the actual value might not compromise the survey respondents' privacy, and in what situation you think they might. And okay, let's hear from some of you, your thoughts. As the database holder, can we give out the actual values? We are, once we have, we are the people who have access to the data, so we will be able to get the exact count. We will know exactly how the rural CUs are there. So the question now becomes, can we give out that value directly? And yes or no, and then why? Anyone have any thoughts to share? Or questions? Let's just say, I think we have about 1,000 observations in the data, okay? And let's just say there are 200, okay? Just use those numbers. Let's just say there are 200 rural consumer units, and we are the people who have the actual value, okay? We know it's 200. Can we release that data? Or can we release that value? If we release it, are we breaking any kind of privacy promise to whoever responded to the survey? And that will be the question. Yeah, Isaac, go ahead.
I was going to say, like, and some of that I imagine would, like, what they signed when they handed over their data for collection. And the other thing too, like Sarah and I talked about, for some things like maybe an address or whatever, it might already be in the public domain. So like that's kind of a loose, like just the broad legal constraints of what like data you have on them and where else it would be.
Right, yeah, so definitely. Yeah, I think typically, or if you and your family are filling out the 2020 census now, I think they will say on their form that like they are under the legal obligation. I mean, the Census Bureau is under the legal obligation not to compromise your answers, your privacy, right? So that will be a typical, like, I mean, the wording that people use. I mean, statistical agencies use when they're collecting data from survey or from census. So here, yeah, so let's just say if the actual values are 200, and in a very unlikely situation, I guess, that if I know, let's just say my neighbor, I don't know if this is a good example, but it could be unlikely but still possible situation that giving out actually just that particular number will inform me certain thing about a particular person I'm trying to find. Okay, even though it might be very unlikely, like I said, but if it's 200, and then if I happen to know about 199 people in that survey who are actually rural CUs, for example, and then so I know it's 199, and maybe I want to know one more person about this situation. I just don't know about that CU's particular urban-rural status. But then if you tell me exact number is 200, then that actually gives me information, right? That actually gives me information about, I know this is probably like a made-up toy example here, very unlikely, but this will be usually people's rationale of, yes, even though the count might not seem to be a very confidential value, but it's still possible to give away certain people's information. Okay. Another way to think about it. So remember the CU data here, the CE data here. They have the income, right? They have the income. So let's just say somebody sends a query and they want to know about the average income of this survey, of this sample. Okay. So if we give out the exact number, for example, and it happens to be, for example, that the richest person in the world is in this sample, then by giving out the average, because that particular person's income or CU's income gonna vastly change the average income, right? So if one person, the richest person in the world or in the US is in the survey or in this particular sample, and the income will be changed a lot by that particular person, right? So then if we give out the average income as it is, then that is, even if you might not know exactly how much that richest person is making, how much the person is making, but it's likely at least to tell you that some super rich people are in the data set. And then that will be a possible way to think about how the privacy is being compromised, even if you think you're not giving something very confidential out. Okay? So in the past, we've been thinking about synthetic data or micro level data because we're looking at record by record, right? We're looking at, well, if I give out this particular person's income or this particular person's expenditure, I mean, obviously we're giving out a lot, like what we used to talk about. But here, like we have seen, we're dealing with summary statistics, okay? And the thing is, sometimes, actually a lot of times, even though you might think that the summary statistics are not that confidential, certain scenarios, I mean, those worst case scenario will still be possible to be arising to show you that, well, giving out the actual values of the statistics might not be safe enough. Okay? So with that in mind, we will see that we're gonna add noise to the query output, okay, for privacy protection. So that means, well, instead of giving out the exact value of 200, I might give out like a noisy version of it. We have to talk about how to add the noise, of course. But the general idea here is that we're gonna add noise. The noise will be very specific to the query that we're doing. And we'll see that how we can add noise that will be guarantee those privacy protection. Okay. All right, the next definition is hailing distance, okay? And differential privacy is actually built up under this very strong, as you can see, assumption, but is not in the strong sense as what we talked about in the past for the risk evaluation. So let me talk about this first. So they say that given databases X and Y, they're the same dimension, okay? And let delta xy denote the hailing distance between x and y by doing this. Okay, so delta x and y, as you can see, is defined to be the cardinality of, or I should say, equation 1 is counting how many records are different across the two databases. Okay, so you see that on the right hand side we have xi does not equal to yi, right? And then we're counting how many i's there are, and that's what hailing distance is about. When we say two records are different, if you have multiple variables, as long as you have anything like maybe one or even more than one variables are different, then you count that those two records are different from each other. Okay? So that's what hailing distance is. And then the strong assumption that I was talking about earlier is that under differential privacy, we add noise by considering the scenario that two databases differed only by one record. Okay, so delta xi equals to 1. Okay, so this will be the case. For example, that we have the CE data, right? We have like about 1,000 observations in total. So this is saying that, let's just say 1,000, okay? And this is saying that except for one record, maybe the last one, let's just say, the 1,000th record, the remaining 999 records between the X and Y, the two databases, they're exactly the same. Okay? Only the last record is different. Okay? So this is what we mean by hailing distance of one of two databases, X and Y. Okay? So as you can see, we make the assumption that X and Y, they're the same dimension. So they all have, let's just say, 4 variables, okay, like in the CE example, and then they all have 1,000 observations. So they are dimension-wise exactly the same, but across the two databases, they're only different by one record, okay? It could be that that one record is having a different income, but it could also be that they have different income expenditure, or like the entire combination is different, okay? So as long as something is different, then the two records are not the same, and hailing distance is counting how many there are, and then differential privacy is under the assumption, the scenario that hailing distance is 1, that the two databases differ by one record. Okay? So this might sound to be a very strong assumption, but I should say it is, and then this is trying to say that, as you will see soon, that differential privacy is really trying to add noise by considering that if two databases only different by one record, we want to make sure that the output, let's just say the count, right? The number of rural CUs that we want to report, that's the query, so we want to give the output. We want to make sure that even though two databases only differ by one record, we want to make sure that the output statistic, which is the count of rural CUs, cannot be differentiated from each other to some degree. Okay. So let me say that again, it might be a little bit convoluted. Differential privacy is trying to add noise to an output, right? Output is query, output the summary statistic, like the count. We want to make sure that I'm working with this data set, the database X, right? I want to make sure that any other database that only differs by one record from my X, any output from there won't be different from the output that I can get from my X to some degree. Okay? So this is the gist of how we think about differential privacy. And of course, you can relax this scenario, right? You can say that, well, what if it's two databases differ by two records, right? So that will be data delta XY to be 2. And then that will be a scenario thinking about two databases differ by two records, and then we want to see how much the difference you will see to the output. Okay? So at the end of the day, we're hoping to show that if two databases only differ by one record, the noisy version of the output that you will see will be bounded in a sense that, well, from the data analyst point of view, you won't be able to tell if, well, if the two databases only differ by one record, you will not be able to tell from the output that you get. And so that is the way how people are thinking about differential privacy. And then, of course, hailing distance is at the core of this assumption. All right, so the fourth definition is called L1 sensitivity. Okay, so a little bit complicated, but bear with us. The L1 sensitivity is the magnitude a single individual data point can change the L1 norm of the function f in the worst case. Okay, so maybe it's easier to look at equation 2. Okay, so f, remember f is the query. Okay, and our output is a k-dimension output, numeric output. So formally, L1 sensitivity of function f, as you can see in equation 2. So let's look at this a little bit carefully. So this notation, the double vertical lines here, this is the L1 norm, okay? And this is, as you can see, the L1 norm between fx and fy. So this is not about x and y anymore, okay? This is about the function, which is the query, which, well, if you think about it, will be the count that we're working with. So this is, the L1 norm is the absolute difference between fx and fy, okay? So if you, once with that in mind, you will see that the L1 sensitivity, which is delta f, L1 sensitivity of function f, it is looking at the L1 norm of fx and fy, the maximum number of that, right? And then given the fact that x and y are in the same dimension and they're only differ by one record. So putting into plain English, that's what the first bullet point is about. The L1 sensitivity is the magnitude. Okay, that's the L1 norm, right? The magnitude, a single individual's data can change the L1 norm of the function. Okay, so a single individual data point, right? And this is being captured by delta xy equals to 1, right? And then, of course, the delta is about f. It is about the function itself. So the function, say, if you're working with a different query, then delta f will be different. Okay? So this is saying that if I'm only having, like I have two databases that differ by 1, what's the maximum possible change of my fx is defined to be my L1 sensitivity. Okay, so we use this notation, and of course, like we were saying earlier, if you have a different query, then delta f will be different. So that's why the L1 sensitivity highly depends on the query that you're making. So let me give you an example. So we will also be able to take the time to discuss with your breakout room members. So if we go back to the CE database, okay, let's just say X is the confidential CE sample. Okay, Y is the database, is another database where only one data entry is different from X. So that is with hanging distance 1 from X. And we know that is delta XY equals to 1, okay? Let's just say our query here is how many rural CUs are there in the sample, okay? So my question for you all is, what is the L1 sensitivity for query F, okay? And if I come back to equation 2, you will see that the definition of L1 sensitivity is in equation 2. So let me put you into breakout rooms to have a quick discussion about what do you think if my F is count, what is my delta F? Okay, so F, remember, is the count of rural CU. Okay, so think about what will be the maximum difference between the Fx and Fy if my X is only different from Y by 1 record. Things might sound a little bit abstract, but bear with us. I think as we go through a couple of more examples, things will become clearer. Okay, so anyone? Any thoughts about what will be the L1 sensitivity for this query, the count query? Will be the maximum possible change of the count if I have two people, one record different from each other. Sarah?
We thought 1 is the maximum change you could get.
So
The change you can get if they're different.
Yeah, so what would be a scenario that we actually get a change of 1?
Well, if X and Y are different, oh, I see. If you change X to Y. Yeah. So if one rural CU became an urban CU, then you would have that change in 1.
Mm-hmm. Yeah, right. So that's what we mean by its maximum, right? So you see that in equation 2, the definition is the maximum change. And so if one record in the data set between, so X is the original, like what we were talking about, right? It's confidential original. And I just say Y is different actually by the record that actually become, it was in X was a rural CU, right? But it happens to be that in Y, it becomes an urban CU. So for that case, the maximum change is 1 in terms of the count, okay? But it's possible that X and Y are different in another variable. Let's just say not about CU, not about the rural urban status or just not changing at all about the count. So it's possible that you just don't have a change at all, right? So the change, which is the L1 norm of Fx minus Fy there, the maximum is 1, but it's possible to be 0. Okay, but it's defined, our delta F, the sensitivity, L1 sensitivity, is defined to be the maximum change. So for any count query, actually, not only just for this example, but for any count query, we're going to have a delta F to be 1. Okay. Sounds good. So let me throw another query to you. Let's just say, yeah, I shouldn't have a, no, I guess, yeah, there shouldn't be a Y here. Sorry about that. I just typo. Cross that out. Just another query F. What is the average income of this sample? Okay. So if I have this query, what will be the L1 sensitivity here? Okay, so think about what will be the maximum change of the income if I have one record different from X. Okay. So that will be the second question. Hey, anyone, what will be the L1 sensitivity for a average query here? Think about the maximum possible change to F if one record is different between the two databases. Anyone? Yeah, Isaac?
Would it be max distance of, or like max in the set, minus min in the set over n? So like pretty much the change in average if you swapped out the max for the min?
Yeah, so that's a good starting point. Yeah, so because we're thinking about the change to average, right? So if you have n records, then if you think about the range, like to say if what Isa was saying that is like the smallest, but to say the extreme case is the small, like the income, the least income becomes the largest income, right? The maximum, the minimum starts to become the maximum. Then the change that will happen to the average income will be the difference of the maximum and the minimum divided by n, because we're thinking about the change to average. Okay, does that make sense to everybody? Yeah, Kevin?
I was just wondering when we're making the second data set Y, like choosing the data entry that's different and what values it has, are there any restrictions on what we can make? Like, for example, income, like does it have to be within the maximum of the first set, or can we make it just like some?
Yeah, good point. That's a great point. So first of all, we're not making any Y. We're just thinking about the worst case scenario. But you're right. I mean, for this case in particular, that we know that we have to divide it by the change by n because it's the income. But what will be the maximum? What will be the minimum? Right? Like say, like what Kevin was saying. Well, my x, let's just say my minimum is, I don't know, 0, and then my maximum in this data set maybe it's 100,000, for example. Then would that just be my range? Like, is it possible that my y can take some even crazier value, like even larger, right, or smaller, like smaller than the minimum here and larger than the maximum here? So, so that's a great point. And in fact, this is one thing I personally think that doing L1 sensitivity here can be a little bit tricky. So people will use, so you see the delta F defined to be B minus A divided by N. Okay, so that part divided by N we know, understand, I think. And B minus A, so B and A actually should be defined in a way that it's not about the minimum and maximum about the data set they're working with, but it's about the minimum possible and the maximum possible of income in the universe. Right? So it is pretty, I mean, to me, I feel like, well, I mean, people might come from, come from different like backgrounds and all that, so they might have different values for B and A, right? So if I'm doing this, or if, and then if Reese is doing that, we might come up with a different delta F, even though we're working with the same thing, right? So, but again, choosing B and A, those values, you should not depend on the data themselves, okay? Because we're trying to think about this scenario that X and Y differ by one record, and for the income situation, it should be a range. It's just like how we are getting the range seems to be, at least to me, I think, very depending. It just simply depends on how the database holder is thinking about the whole thing. Okay, so that's a good thing to note. One thing about the count query, like we saw here for the first one, is, well, regardless of what kind of count you're working with, delta F is always 1. Okay, so that one is sort of set in stone. It makes sense. But if you start to do certain things about, like, say, numeric query, like in this case, income, and then we know that to the average income, the change, the maximum change, is the range divided by n. So the range should not be depending on the data we're working with, but should be, well, depending on your own evaluation. But then that thing could be varied a lot from people to people. Okay. So keep that in mind. That's a great question, and I good to see that we came together to the conclusion from various discussion. Okay, so in sum, L1 sensitivity, it depends on, yeah, it depends on the database itself. Okay, and the query sent to the database by the data analyst. Okay, so when we say data depends on the database, it's not so much about how to set up B and A. Like we said, you should not depend on the database itself when you think about the possible value of the maximum and the possible value of the minimum. But it certainly depends on the query itself, right? And then, of course, when we say depends on the data base, is thinking about, well, we're talking about CU, consumer unit in the United States. So even though values of B and A can be come up by yourself, like with all kinds of range that you can think of. But again, we are talking about in the United States, the possible smallest value of income and the possible largest value of income. So that, again, the L1 sensitivity still depends on what the database is talking about, right? So that's what we mean, okay? So L1 sensitivity, as you can see, is depending on the query and the database. So, and we have summarized at least the two cases here that if we're working with count query, it's going to be delta F equals to 1. We're working with average income, it's going to be delta F equals to B minus A divided by N. And you can naturally also think about, oh, what if I'm thinking about query of standard deviation of income, right? So think about, the formula of coming up with standard deviation and then factor that into delta F. So for simple statistics, coming up with delta F should be overall straightforward, but we still should think carefully as we move along, okay? All right, so with all of this in mind, we're finally able to define epsilon differential privacy. Okay, so bear with me. So we want to guarantee a mechanism, okay, we call it mechanism, think about it as a technology, or just a way to deal with adding noise. Okay, we want to guarantee that a mechanism behaves similarly, meaning that it will give very similar outputs on very similar inputs. That is when two databases differ by 1. Okay, so this goes back to what we were talking about slightly, or just a few slides ago, when we were trying to think about L1 norm or L1 sensitivity in the first place, right? We are considering very similar inputs, right? When two databases differ by 1, that is when their Hamming distance is 1. We want to add noise in a way that the output will be very similar, okay? Because through that, you can guarantee that the data analyst, like the receiving end of the output, won't be able to tell or won't be able to differentiate like whether somebody's in the database or et cetera, okay? So the particular approach differential privacy is taking is that they're trying to bound the log ratio of the probabilities of the outputs from above, okay? So you will see soon in the expression that would take the log ratios of the probability of the outputs, okay? So when you think about X and when you think about Y, we're gonna take the log ratio of those probabilities from, and we bound it from above, and then give the upper bound on the noise added to the output to the output to preserve privacy. Okay, so we first of all going to bound it from above, and then we're going to be basing on that to add the noise. Okay, so bounding it from above, let me show you here. Bounding it from above is to make sure that we get similar outputs, right? Similar outputs that they're only differing to certain degrees. So if you look at equation 3, so we use this curling M, denote mechanism, okay? And we use this epsilon. We're going to define this epsilon in a second, but think about it as a very small number, just as what we usually do in calculus, right? So epsilon differential privacy, you think of all Hamming distance 1 databases, X and Y, right? Their delta XY equals to 1. So look at what we're doing here. We're taking, we can think of probability of MX, right? Over probability of my, so think about they're just like probability of getting this output, okay? We take the ratio and we take the log of it, take the absolute value and bound it above, okay? So another way to write this, as you could imagine, so some people like to work on the log scale with this expression, but some people would do graph MX. So S, by the way, is the range of M, so all of the possible values of M. So you can do this, and Y, and S, right? And then this will be bounded above by E to the epsilon, right? If I don't take, I mean, if I take exponentiation on each side, okay? So that would be another way to think about it. So this one may be more intuitive, depends on which one you're thinking about. So the one that I just wrote in red, this is the ratio, right, of the probabilities, okay? And we bound it above by E to the epsilon power, okay? Or in other words, we take the log of it and it's bounded above by epsilon. Make sense? Make sense? I just realized I probably don't really need the absolute value here, since both of these are probabilities, right? But when I take the log, we need to make sure that we take the absolute value. Okay? So here, think about that. Well, this is a bound. This is the maximum difference in terms of the log ratio of probabilities that we allow the output to have. Okay? So taking the upper bound gives us the maximum possible possible value, right, of the change of the ratio, the log ratio. And this is a way to think about, well, we're bounding from above, how the two outputs could be different from each other, right? We do not allow it to go above this bound. Okay? And that epsilon is how we're going to bound it. Okay? And that epsilon, as you will see, it goes into the definition of epsilon itself, right? Epsilon differential privacy itself. Okay? And epsilon itself is called the privacy budget. We're going to define it next. And bound the ratio above by epsilon, as we have seen, is setting the maximum difference that you will allow it to happen to the outputs. Okay, so the last bullet point here, epsilon differential privacy provides us a means to perturb the output, adding noise, okay, by adding noise, so that similar inputs produce similar outputs under the mechanism M. Things might sound very abstract or a little bit vague, but formally, this is how we define it. The key here is that we want to make sure that if I have very similar inputs, I want to have very similar outputs. Okay? Because only by doing that, we're able to provide a privacy protection, because similar outputs should give you similar, similar inputs should give you similar outputs. So we don't want to like let it go extreme, and then that might compromise the privacy. Because like going above certain bounds, like epsilon, for example, then we are giving out information. Okay? And the way that we're doing it is we are bounding the log ratios of probability, okay, above by a small number epsilon. Okay? So as you will see, well, how can we define epsilon, right? And then so far we haven't been talking about, well, how can we make sure that, like, how can we add random noise? We just know the definition here, right? What is the process of getting a random noise involved in this case? Okay? But get the idea that we're trying to guarantee a mechanism behaves similarly on similar inputs, and we're bounded above of the log ratio probabilities of the outputs by epsilon. All right, the last term. Finally, okay, it's the privacy budget. It's epsilon itself, okay? It is predetermined, okay? So think about that. Well, before I decide to release the noisy version of the count to the data analyst, I need to be told a lot of times, or I have to select a privacy budget that I'm willing to work with. And we call it privacy budget, and we also say that it to be spent by the data holder when answering queries. Okay, so there are certain things involved about how to spend the privacy budget epsilon. For example, like if I only have one question to answer, can I spend all of them on my only one question? Or what if I have two questions or multiple queries to be answered? Then how can I spend my privacy budget? Like, do I spend them evenly, or et cetera, et cetera? Okay, so in short, the privacy budget is predetermined, and it will be spent, depends on how we're gonna spend it. But well, it's budget, so we use the word spending.